The major desire of a pilot is to fly a specified course and land at a pre-planned destination. To do this, he or she must apply basic fundamentals of navigation. In the next two programs, we'll discuss two basic forms of navigation, pilotage and dead reckoning. Pilotage is flying by observing visual landmarks such as railroad tracks, major highways, rivers, and towns to establish one's position. Dead reckoning derives its name from the term deduced reckoning, which was abbreviated to DED, dead reckoning. The pilot determines position by means of calculating a record of time, distance, direction, speed, and wind. Dead reckoning does not rely on visual landmarks, but uses them to verify the calculations. We need a basis from which to measure time, distance, and direction, and long ago the sphere we live on and fly around was carefully divided by lines of latitude and longitude. Latitudinal lines start at the equator and parallel each other northward and southward to the poles. These lines of latitude are called parallels. The longitudinal lines start at the prime meridian, which is a line running from the North Pole through the observatory at Greenwich, England, and to the South Pole. If this line or meridian is continued from the South Pole past the equator to the North Pole, the line forms the international date line where one day ends and the next begins. The prime meridian is a reference to measure longitude east and west to 180 degrees at the international date line. The lines of latitude and longitude intersect to form a grid system, and you can locate any point on Earth by naming the meridian and the parallel which pass through it. Let's try out the system. If I told you to find the city located at 90 degrees west longitude and 30 degrees north latitude, you would pinpoint New Orleans. At 105 degrees west longitude and 37 degrees north latitude, you'll find Denver, Colorado. At 124 degrees west longitude and 47 degrees north latitude, you'll find Seattle, Washington. Now let's see how this process transfers to the sectional chart which we use for navigation. If we are told that Point Reyes is located at 123 degrees west longitude and 38 degrees north latitude, we can locate it by finding the markings on the border of the sectional chart and following them to their intersection. And here is Point Reyes. The latitude and longitude lines are labeled for each degree interval. Each degree is then divided into 60 segments called minutes. Every 10 minutes there is a large tick mark on up to 30 minutes where the number is indicated on the chart, then on up to 40, 50, and 60 minutes indicating the next degree. So you can very precisely pinpoint any position. Let's do a few examples. San Francisco Airport is located at 122 degrees, 23 west, and 37 degrees, 37 minutes north. Follow the lines along until they intersect, and here is San Francisco Airport. San Carlos Airport is located at 122 degrees, 15 minutes west, and 37 degrees, 31 minutes north. Follow the lines until they intersect, and here is San Carlos. Half Moon Bay Airport is located at 122 degrees, 30 minutes west, and 37 degrees, 31 minutes north. Again, follow the lines to Half Moon Bay Airport. Using latitude and longitude, you can locate any place on Earth. Another factor of navigation is time. We know there are many time zones around the world, so that we need one international form of time. International time uses a 24-hour clock to avoid the confusion of duplicating AM and PM hours. Time on a 24-hour clock is given in 4 digits, with the first 2 indicating the hour and the last 2 the minutes. Hours are numbered from 0 to 24, starting at midnight. Examples of time in the morning are 0000, which is midnight, 0815 or 8:15, 1100, 11 o'clock. Time in the PM period is expressed as 1300, which is equivalent to 1 o'clock, 2115, which is 9:15. The 24-hour clock starts at the prime meridian at Greenwich, England, which is why it is called Greenwich Mean Time, or GMT. However, the aeronautical world uses Zulu for GMT. Time zones generally correspond to the meridians because our Earth turns 15 degrees each hour, but they are adapted to accommodate geographical areas. Since an aircraft can pass through many time zones on a flight, we need to know how to convert to Zulu time to avoid the confusion of time changes. Our primary interest is in the 4 time zones within the continental United States: Eastern Standard, Central Standard, Mountain Standard, and Pacific Standard. To convert to GMT, or Zulu time, add 5 hours to Eastern Standard, add 6 hours to Central Standard, add 7 hours to Mountain Standard, and add 8 hours to Pacific Standard Time. We also need to know how to read and interpret the charts used to navigate. Sectional charts are most often used by private pilots. They show topography, terrain features, man-made features, and give aeronautical information. The scale is 1 to 500,000, or 7 nautical miles to an inch. The relief features are color-coded from pale green at sea level to brown tones for the highest terrain. The face of the chart indicates the highest terrain and its location by latitude and longitude, in this case 14,495 feet. In addition, the chart shows maximum elevation figures within each grid bounded by latitude and longitude lines. It is shown in thousands and hundreds of feet above mean sea level. The figure shows 4,200 feet. The figure represents the highest known obstacle in each grid, including terrain, trees, towers, and antennas. Hydrographic information is anything related to water areas, helpful to navigation and are color-coded in blue. Included are location of dams at lakes and rivers. Shorelines of the oceans and bays show specific contours. Inlets and points of land are also shown, as well as piers and easily identifiable rocks. Bridges and roadways or viaducts which cross waterways are shown in magenta, and railroad tracks and railroad bridges are shown in black. Roads are indicated in magenta, the thickness of the marks indicating whether it is a major roadway, a freeway-type divided highway, or a smaller road. Some of the major highways have identifying markers along the highway showing the numbers of that highway. Railroads are marked in black with cross-marked single or double tracks. Power transmission lines are also black with towers spaced every so often along the lines. Yellow is used to indicate cities and towns, generally outlining the shape of the outskirts and indicating the overall size of each city or town. Very small towns are marked with a black circle. Easily visible ground objects such as racetracks, outdoor theaters, and tanks are shown with appropriately shaped symbols. Of course, one must know and recognize airports if we are to find the way to a specific destination. Uncontrolled airports, those with no tower, are shown in magenta. Controlled airports, those with towers, are shown in blue. An airport with a paved runway more than 1,500 feet long will be shown with runway pattern. All recognizable paved runways, including closed runways, are shown with visual identification. The airport will have printed data nearby in either magenta or blue color. Uncontrolled airport data is first the name of the airport, Antioch. Next line is the elevation in feet above sea level, 185, an L if lights are available on the field, a dash if not. Next information is the longest runway length in hundreds of feet. 25 equals 2,500 feet. And the frequency for Unicom, if it is available, 122.8. Controlled airports have additional information regarding radio frequencies. After the airport name is the control tower frequency indicated by CT and the appropriate frequency. The next line has the word ATIS standing for Automatic Terminal Information Service, and next to it the appropriate frequency where ATIS is available. The next line is the same as uncontrolled airports with the field elevation, 244, the L indication of lights if there are any, the longest runway length in hundreds of feet, 6,600, and the appropriate Unicom frequency. If there is a flight service station on the field, the letters FSS will be above the airport data. There are many other types of airports, each identified with different symbols on the sectional chart. Civil and public use airports are the ones you will most often use. This R symbol indicates a restricted non-public use airport. It may be used for emergency only and is a good landmark for navigation. Some private airports are not restricted and just have the abbreviation PVT by the name. Abandoned airports are indicated with the airport symbol and an X marked through it. Not usable except in emergency, but a good navigation landmark. Unverified airports are indicated with a U in the center of the airport symbol. Heliports have an H in the center of the symbol. And seaplane bases are indicated with an anchor inside the airport symbol. You have already been introduced to several other symbols with which you will become familiar as you use the charts. We are shown special use airspace on the charts by solid blue lines marking the boundary with diagonal blue lines inside the border area. The number and type of each special use airspace area is adjacent and is lettered in blue. The letter P, Papa, stands for prohibited space and indicates an area within which flight of aircraft is not permitted, usually because of national security or national welfare, such as space over the White House and the Capitol area. R is a restricted area of airspace where flight is subject to limitations. These areas denote hazards to aircraft, such as artillery firing, flight of guided missiles, some of which may be heat-seeking, so our hot little engines would be a great attraction. Very hazardous areas to fly without authorization. W indicates a warning area. Activities may be the same as within a restricted area, but the space cannot be so designated because it is over international waters. These are established beyond the 3-mile limit. Alert areas indicate airspace in which pilots should be on the alert for military activity. MOA is a military operations area. A high volume of military pilot training occurs here. Hours of usage and altitudes of the operations are printed on the chart, as is the facility contact regarding the activity, so the pilot can decide whether to fly through the area or not. A pilot doing so is totally responsible for collision avoidance. Information regarding hours of use, floors and ceilings, and facilities to contact for further information about these areas is given on the border of the sectional chart. Now let's put this information to use to navigate from San Carlos to Modesto. The first step is to select the valid current issue chart for the area of your flight. Dates and the area covered are shown on the face of the chart. Then mark the course on the chart using the navigational plotter. The plotter consists of a straight edge with scales for various charts and both statute and nautical mile measures. A protractor is part of the plotter also and is usually attached on the upper edge. Line up the center of Carlos Airport with the center of Modesto Airport and draw a line connecting the two. This is the true course line, the path you wish to fly in the airplane. Now you must check to make sure the course does not pass through any special use airspace, and you must check for the highest terrain on the route. Now we need to determine the true course, the angle between our course line and true north. To measure the true course, find a meridian as near as possible to the center of the course line. This meridian will be used to measure the number of degrees to fly to the destination. Place the small hole of the plotter over the line where the course line and meridian intersect. Make sure that the upper edge of the plotter is along the true line. Now use the meridian as an index to read the number of degrees shown on the protractor. The course line is 83 degrees. We use the outer scale if the destination airport is to the east of the meridian, and the inner scale if the destination airport is to the west of meridian, as these arrows indicate. Next, we need to know the distance from San Carlos to Modesto. Using the mileage scale indicated for sectional charts, we place the plotter along the course line from San Carlos to Modesto, and reading on the outer scale, we find it's 62 nautical miles to Modesto. Now, with the distance scale still in place, mark off every 10 miles along the course line with tick marks. These will be helpful in choosing landmarks to be used as points, in calculating distances quickly, and monitoring fuel and time en route. Now comes the selection of prominent visual landmarks. These will be our checkpoints. After takeoff, we see the contours of the bay, the towers on the east side of the bay, and the divided highway. Next good checkpoint would be the Sunol Golf Course and the lake just to the left of course at 20 nautical miles. It will be easily identifiable and close to our course, an excellent checkpoint. Further along the course is a second lake, also an excellent visual reference. The next good checkpoint would be the intersection of the double divided highways in the foothills just over the mountain ridge, approximately 43 nautical miles along our course. Good landmarks beyond that are the two canals, the abandoned airport, a smaller highway paralleling railroad tracks and crossing over the tracks, the towers just before the city of Modesto, the city itself, and then the Modesto airport. The limitation to pilotage, as you have probably already figured, is visibility. Hazy conditions can be a problem and create lack of suitable landmarks. Another form of navigation which solves some of the pilotage problems is dead reckoning. It begins with the same basic procedures as used for pilotage. Determine the true course line on the current nautical chart. Remember how we did it before, drawing a line between the two airports. Measure the true course in degrees by reference to the meridian near the center of the track, making sure the top edge of the plotter is along the course line and reading the degrees at the top of the protractor. Place the mileage ticks on the chart and appropriate checkpoints. Then come the additional computations involved with dead reckoning. First, we must find the true heading by using the winds aloft forecast to determine the size of the wind correction angle. If the wind is blowing from the side, we will not be able to track on our desired course by flying along the true course line. So the nose of the airplane must be angled toward or into the direction from which the wind is blowing, and the method for computing this will be taught in the flight computer portion of the telecourse. For now, we need to know that if the crosswind is from the left, you subtract the wind correction angle from the true course to obtain the true heading. If it is from the right, you add the wind correction angle to the true course to obtain true heading. To achieve a true course of 85 degrees with the wind blowing from 5 degrees to the right, you must fly a true heading of 85 plus 5 or 90 degrees. However, the magnetic compass uses the magnetic North Pole rather than the true North Pole, so we must account for the difference between them. This difference between true and magnetic north is called variation. It is marked on the charts with dashed magenta lines. The 0-degree variation line is called the agonic line, the others are called isogonic lines, and the number of degrees variation is shown along each isogonic line. These lines are irregular, unlike meridians, and your course may cross through different variations, so this must be considered in your computations. Western variation is added to the true heading, and eastern variation is subtracted. One of the axioms to assist in remembering this is, east is least and west is best. So to achieve a magnetic heading in the vicinity of Monterey, we find 16 degrees east variation. We would subtract, east is least, 16 degrees from the true. Our computations need one more step to be complete. There are errors in the magnetic compass readings due to metal parts of the airplane, the ignition system effects, and interference of airborne radios. This error is called compass deviation, and the amount of deviation is unique to each aircraft. So you will find a compass correction card mounted in the cockpit, usually on or near the compass, indicating what compass heading to steer to achieve the proper magnetic heading. Using our same cross-country flight that we used for pilotage, let's add the dead reckoning techniques to accomplish the flight. The first 3 steps are already completed. Draw the course line on the chart, mark the tick marks, and read the true course from the top of the protractor of 083 degrees. 3 additional steps are the wind correction angle to compute true heading, variation to compute magnetic heading, and deviation to compute compass heading. Assume a wind correction angle of 5 degrees right. This means it is added to the true course for a true heading of 088 degrees. Variation in our course area is 16 degrees 30 minutes east. Remembering the rhyme, east is least, west is best, we subtract 16 degrees 30 minutes for a magnetic heading of 071 degrees 30 minutes. Next step is to consult the compass deviation card and add or subtract from the magnetic heading to compute the compass heading. For example, we would steer 57 degrees to fly a heading of 60 degrees using the card. For values between the published figures, we must interpolate or find the difference between the given values. For 60 degrees, we are told to steer 57 degrees or -3. For 90 degrees, steer 86 degrees or -4 degrees difference. Note that 71 degrees 30 minutes is close to half the difference between 60 and 90 degrees. So if we use half the difference between the values given for the compass heading, we have 71 degrees 30 minutes minus 3.5 degrees, or 3 degrees 30 minutes, and our compass heading is 68 degrees. Knowing the wind conditions, we can do further calculations regarding time and distance to compute ground speed, our actual speed over the ground track. These calculations give us figures by which we can estimate time en route, time of arrival, and the very important aspect of fuel consumption, without which we might have a surprise landing. After determining ground speed, which will be explained in detail in later segments, the idea is to use the formula time equals distance over ground speed to determine the time it will take to complete your trip. For example, if we compute the ground speed for our trip Carlos to Modesto as 124 knots, it will take us 30 minutes to cover the distance of 62 nautical miles between the 2 points. Once en route, the same formula can be used to determine our actual ground speed, compared to the ground speed calculations based on the forecast winds. Let's try another trip. It takes 3 hours to travel 270 nautical miles. Dividing 270 by the time, 3 hours, ground speed is 90 knots. This ground speed of 90 knots is the basis for estimating the time at which you should reach the next checkpoint or the destination. If your actual ground speed is different from what you expected, you will need to do some recomputing to determine revised time en route. Time, as we've said, is computed as distance over ground speed. So if the distance to your destination is 210 nautical miles and ground speed is 90 knots, the time to get there would be 2.3 hours. One can also determine distance flown by using the formula distance equals ground speed times time. If ground speed is 90 knots and you have flown for 2 hours, the distance covered would be 180 nautical miles. The ever-important aspect of fuel consumption is determined next. A pilot must know the average rate per hour of fuel consumption for the particular airplane he or she is flying. By using the formula fuel equals time times rate of consumption, we can compute fuel consumed. Suppose we want to fly 400 nautical miles with a ground speed of 100 knots. Using the formula for time, time equals distance over ground speed, we arrive at a time of 4 hours. Our rate of consumption is 5 gallons per hour, so we multiply 4 hours times 5 gallons to determine 20 gallons of fuel. We will put all of this information to use in the preparation of a short cross-country in the next program. It is important to remember that a good flight begins on the ground with thorough flight planning. On the previous program, we discussed pilotage and dead reckoning, two basic forms of navigation. Now let's put those techniques to work by flight planning a short cross-country flight. Remember the closing statement of the previous program that a successful flight begins with thorough pre-flight planning. That's how we'll begin this flight. Get out your equipment and follow along this time. You will need a current San Francisco sectional chart, a plotter, the airport facility directory or a flight guide, a flight planning sheet on which to enter all of your computations, and a pen or pencil. The flight will be from San Carlos to Modesto in California. San Carlos Airport is located at 122 degrees 15 minutes west longitude and 37 degrees 31 latitude. Modesto Airport is located at 120 degrees 57 minutes west longitude and 37 degrees 38 minutes north latitude. The conditions for this flight will be as follows. Write them on a sheet of paper to have for reference. Takeoff time will be 0900 Pacific Standard Time. Cruising altitude will be 5,500 feet. True airspeed will be 97 knots, and indicated airspeed is 89 knots at 2,500 RPM power setting. The weather check with the Flight Service Station, which is required, shows weather conditions are clear and visibility unlimited, or CAVU, CAVU in the aviation vernacular. These are ideal conditions for beginning pilots, especially if the winds are calm, as they are for this trip. The temperature is plus 4 degrees centigrade. Fuel at 2,500 RPM is 6.2 gallons per hour. With you and the flight instructor and full fuel on board, the airplane is within the proper weight and balance requirements. The compass deviation card, which we will use for computations, reads as shown. Prior to takeoff, we will complete the flight planning sheet, computing the estimated time en route, or ETE, our estimated time of arrival, or ETA, the fuel requirements for the flight, the checkpoints to be used for navigation, and complete the other information indicated. In addition, we will list all the communication frequencies for the flight and traffic pattern information for both airports. Using the plotter, mark the course on the current San Francisco sectional chart. Line up the plotter on the center of each airport and draw the line between the two airports as we did before. Then find the appropriate scale for sectional chart and for nautical miles and measure the distance from San Carlos Airport to Modesto Airport. We see that the course is 62 nautical miles. With the plotter still in place, mark off the tick marks every 10 miles along the course. For long cross-country flights, it's helpful to mark off each 50 miles along the route for easy computation of total distance flown as the flight progresses. Look over the course line to see if it passes through any special use airspace. We're very close to R2531, but the course does not pass through it. Look at the terrain to be sure the proposed altitude of 5,500 feet will be clear of terrain and of any obstructions. The highest terrain near our course is the mountain peak at 3,607 feet, slightly right of course. The proposed altitude of 5,500 will allow ample terrain clearance. It is important to find checkpoints on both sides of the course in order to determine if you are remaining on course as desired. If you are on course, hold the same heading and continue on course. If the airplane's track is not on the course line, you must change the heading to put the airplane back on the course line before reaching the next checkpoint. Otherwise, you might miss the next checkpoint and chance getting lost. Remember that prominent checkpoints are those most suitable and easily spotted from the air. Our first checkpoint on course happens to be marked with a small magenta flag, since it is a visual checkpoint in the San Francisco Terminal Control Area. In this case, the flag identifies transmitter towers adjacent to a bridge and a railroad bridge. The town of Newark on course, but is hard to find a specific thing to pinpoint, so continue on across town to the double railroad tracks, which looks rather prominent, followed by a divided curving highway. There's another magenta flag at the Sunol Golf Course 2 miles left of the course. A double row of power lines crosses over the course. A lake on the left of the course is within 2 miles. The reservoir off to the right is twice as far, and further along a second lake on the left. Another power line crosses the course, and Tracy Airport is to the left of course. The course crosses a divided highway at a Y intersection with a second divided highway. Next, there are 2 canals which we will cross, an abandoned airport on the course, a single railroad track which is paralleled by a highway which then crosses over it and continues paralleling it on the other side. Towers to the right of the course of the city of Modesto, and finally the Modesto Airport itself. There's no trouble using pilotage on this course. We have excellent visual checkpoints. The next step is to determine the true course of the flight. Locate a meridian near the center of the course line. Place the small hole in the center of the plotter on the meridian, making sure that the straight edge of the plotter is aligned with the course line. The destination airport is to the east of the meridian, so the outer scale will be used to read the true course, which is 85 degrees. Notice the arrow shows the course direction. At this point, we should begin to put our figures on the flight planning form to keep the information organized and at our fingertips. A flight planning chart is a valuable aid to assist in keeping all pertinent information where you can best use it. If you plan a flight properly, no surprises along the way. The route is San Carlos to Modesto, so we enter that information using the three-letter code for each airport. SQL for San Carlos, MOD for Modesto. I hope you are following along with the flight planning and filling in the information on your flight planner. These techniques are most easily learned by doing. We know the distance to be 62 nautical miles, so we enter that figure. We have just determined the true course to be 85 degrees. Enter that. Further information we already know is the temperature, 4 degrees centigrade. Altitude, 5,500 feet. Indicated airspeed, 89 knots. True airspeed of 97 knots. Calm winds, so we enter 00. Proposed time of departure is 0900 Pacific Standard Time, or adding 8 hours, 1700 Zulu. Now we must compute the figures needed to use the techniques of dead reckoning. Wind correction angle computations will be taught later in the flight computer portion of the telecourse. With a calm wind, there is no wind correction angle, so we enter 0 degrees. To determine the true heading, we would add or subtract the wind correction angle. Since it is 0, our true course and true heading are the same, 85 degrees. Variation is shown on the chart with dashed magenta isogonic lines. So we look on the chart in the vicinity of the course line and see 16 degrees east. Enter 16 degrees under variation. Remembering that east is least, subtract 16 degrees from 85 degrees, the true heading, and enter the magnetic heading of 69 degrees. Using the compass deviation card, we note it is necessary to steer 57 degrees for a magnetic heading of 60 degrees, or a difference of -3. Next increment given is to steer 86 degrees for a 90-degree magnetic heading, which is a difference of -4. Since there is just 1 degree difference, and 69 is close to 60, we'll subtract 3 degrees from the magnetic heading to determine compass heading of 66 degrees. The next column is for ground speed. Ground speed is the actual progress over the ground of the aircraft. If there is no wind, true airspeed and ground speed will be the same. With a tailwind, airspeed, the movement of the aircraft through the air mass, remains the same, but the speed over the ground will increase. A 20-knot tailwind will increase ground speed by 20 knots. A headwind will decrease ground speed. So with 20 knots headwind, airspeed again will remain the same, but ground speed will be changed by -20 knots. Computing by using wind direction and velocity is also part of the computer portion of the telecourse. In this instance, the wind is calm, so ground speed and true airspeed are the same, 97 knots. This information is the basis for estimating the time to each checkpoint or destination, the time en route, the estimated time of arrival, and the fuel consumption, the dead reckoning aspects of the flight. Using the formulas already introduced, we determine the estimated time en route. Distance is 62 nautical miles. Ground speed is 97 knots. Dividing 62 by 97 gives us 0.64, or 64 1/100ths of an hour, which we multiply by 60 minutes to find our estimated time of 38 minutes en route. Since we won't be flying at 97 knots until we've completed our climb and are at cruise, the general rule of thumb is to add about minutes for the climb, making an estimated time en route of 43 minutes. Enter the time in the ETE column. Considering the departure time of 0900, the estimated time of arrival will be 9:43. Note that these are estimated times, and there is a specific place for the actual time of takeoff, the actual time en route, and the actual time of arrival. Those figures are entered as they occur in the flight. The fuel consumption is next to be considered. The time en route is calculated as 43 minutes, or 72 hundredths of an hour. The rate of consumption is given as 6.2 gallons per hour. Using the formula given previously, fuel equals time times the rate of consumption, we have 0.72 times 6.2, which equals 4.1 gallons. Regulations require a 30-minute reserve for cross-country flights, so we will need 3.1 gallons plus the 4.5 gallons, computed for a minimum of 7.6 gallons to be carried for this trip. Much of the flight planning data is now complete, but we need to have every bit of information possible regarding each airport: the radio frequencies needed for communications, flight advisory frequencies, and weather frequencies to check en route. Using the airport facility directory, check to find San Carlos and Modesto airports. Listings are by state and then alphabetically by airport name. The ATIS, Automatic Terminal Information Service, for San Carlos is 125.9. Enter on the chart. Ground control frequency, 121.6. Tower is 119.0. Traffic pattern altitude is 800 feet L. Elevation, 2 feet. Look for any other information which may be of importance to your flight. Next, repeat the same procedure for the Modesto Airport. No ATIS here. Control Tower 120.0, Ground Control 121.7. Traffic pattern altitude is 900 feet MSL, and elevation 97 feet. Under the Remarks section, enter the frequency to contact Oakland Radio, 122.5, to activate the flight plan. Approach control frequency for flight advisory services is 120.1. And Flight Watch for in-flight weather advisories is 122.0. Notice the reminder to close the flight in 30 minutes of your ETA, otherwise search and rescue procedures will be started. A flight plan is not an FAA requirement for visual flight, but is highly recommended as good operating practice. Also, another recommended practice which we must omit due to time is planning for flying to an alternate destination in the event of unforecast bad weather or other factors. Here is the FAA flight plan form. You complete the information as indicated and file by phone with the nearest flight service station. Flight service station then gives you a frequency to contact for activating the flight plan. When the pre-flight planning is completed and you are satisfied that you have all the needed information, take all your paperwork and head for the airplane. After completing a thorough pre-flight inspection, we taxi to the designated runway, take off, and become airborne. Remember to note the actual time of takeoff and enter it on the flight planning sheet. When we're clear of the airport traffic area, we call flight service to open our flight plan. Oakland Radio, this is Skipper 37259er. would you activate our VFR flight plan from San Carlos to Modesto, departure at 0900. As we depart from the traffic pattern and begin to cross the bay, the first checkpoint is the two bridges located right of our course. There they are. Next, locate the transmitter towers. There they are. Check your chart and verify the position. The next checkpoint you can clearly see is this highway winding its way through the hills right of course. Here's what it looks like. Left of course on our chart is the Sunol Golf Course. As you can see, it's an excellent visual landmark. Our next checkpoint is this lake, located left of course. Over to the right is a reservoir. There it is. There are three lakes located very close to our course. This one on the left is very distinctive. It's long and narrow with a dam positioned at the far end. Coming up right of course should be this mountain peak. It's the highest terrain in the area. Remember to constantly cross-check outside visual references against the information on the sectional chart as you progress to the next checkpoint. Tracy Airport is coming up next, about 6 miles to our left. Just ahead is a divided highway and the Y intersection and another divided highway. This makes another excellent checkpoint. Next are the two canals, almost perpendicular to our course. There they are. Here's an abandoned airport which our course line crossed. Referring to the chart, our next checkpoint is the railroad tracks and the road crossing it. You can see from the smoke that surface winds are in our favor and we appear to have a slight tailwind. This is a very useful piece of information. On our chart, there is a long row of power lines. These lead right into Modesto. Here we are over the outskirts of Modesto. Beyond the city lies the airport itself. As you approach the airport, check the direction and numbers of runways as indicated on the chart. Modesto Airport has 2 runways, parallel but offset. So this definitely is Modesto. Check your arrival time. It's a few minutes short of the 43-minute arrival time, but we haven't landed yet, so we are probably on time. We have landed safely in Modesto, traveling point to point using pilotage. We call Stockton Flight Service through a remote unit located near the Modesto Airport to close our flight plan. Stockton Radio, Skipper 37259er.
Skipper 37259er, go ahead.
259ers on the ground at Modesto. Would you please close our VFR flight plan from San Carlos?
259er, understood, on the ground at Modesto. We'll close your flight plan from San Carlos. Good day.
If a wind change had occurred and you became aware that you were being blown off course, you would alter the heading to compensate so that you remained on course. And dead reckoning is incorporated into the flight with the computations made in the pre-flight planning, plus ongoing calculations. At takeoff, the time was noted and entered in the actual takeoff column, 0900. En route, the ground speed is computed between checkpoints. If the ground speed is not the same as estimated, an adjustment is made in the ETA to the next checkpoint. In addition, TE is changed, and the ETA at destination would change also. For example, when we reach the first lake on the left of course, we should be at cruise level. If we start a time check from the lake to the Y in the double highways, we can compute actual ground speed. As we are flying, we use the tick marks to calculate the distance between the 2 points, approximately 23 nautical miles. The timing is 15 minutes between the 2 points, and we use the formula ground speed equals distance over time. We convert the minutes to mathematical terms. 15 minutes equals 1/4 of an hour, or 0.25. Dividing 23 nautical miles by 0.25 equals 92 knots ground speed. This is slower than our estimated ground speed of 97 knots. So recalculate the remainder of time en route and time of arrival. These computations will become clearer when we discuss the use of the computer. For ground speed checks, choose the first checkpoint close to departure after level off, then other checkpoints at 20 to 30 mile intervals. In general, pilots use a combination of pilotage and dead reckoning techniques, calculating the airplane's position and visually checking selected landmarks. We'll use these in depth in the cross-country programs and include the techniques of radio navigation, which will be discussed in the next program. Radio navigation means using radio signals broadcast from ground-based stations. With these signals, we establish radio navigation courses or determine our position. The Very High Frequency Omnidirectional Range Station is the heart of our national system of radio navigation. Abbreviated VOR, there are more than 1,000 of these stations throughout the country. Each transmits 360 electronic courses called radials, and selected radials from each station magnetic lines of position. A single VOR may be the hub for a number of airways. These airways converge at the VOR. Although due to space limitations on the sectional chart, they are only drawn to the compass rose surrounding the VOR. VOR airways are numbered, as highways are numbered. Each number is prefixed with the letter V for Victor. This informs the pilot that the airway is formed by a VHF navigation aid. VOR stations transmit on any one of 200 frequencies in the VHF spectrum between 10800 and 11795. The VOR receiver in the airplane electronically measures the angle between magnetic north and the line of position on which you are flying. The VOR puts out two signals. One is the all-directional or omnidirectional signal. The omnidirectional signal is timed to transmit at the same moment the rotating passes magnetic north. Your VOR receiver electronically measures the difference. This time or phase difference is then translated into the number of degrees between your position and magnetic north. There are three symbols used on aeronautical charts to depict VOR stations. The one most frequently observed is the VORTAC, a combined VOR and military distance measuring equipment known as TACAN, a contraction for Tactical Air Navigation. The upper symbol illustrates the geographic positions of VORs, and the symbol with the box around it represents VORs combined with civilian distance measuring equipment, or DME. Our discussion in this program will be restricted to the VHF omnidirectional range portion of these facilities. Most VOR stations on charts are surrounded by circles called azimuths. Azimuths depict points of the... Though there are 360 radials transmitted by each VOR station, the azimuths have space to number these radials only every 30 degrees. Every 10 degrees, a long tick mark indicates 10-degree increment, while a shorter tick mark indicates a 5-degree increment. The individual radials are not marked on the chart, although you can fly so precisely using the VOR that you will almost always select exact radials. A common student misinterpretation of the chart data is that the azimuth indicates the limits of reception of the VOR. Not so. Signals can be received for up to 70 miles dependent upon your altitude. This Victor airway, numbered 338, demonstrates how precisely you can navigate using VOR. The airway is formed by the 202-degree radial of Lake Tahoe VOR. You may fly either outbound on the airway with a magnetic course of 202 degrees, or you can fly inbound on the airway, in which case your magnetic course would be the reciprocal of 202 degrees or 022 degrees. However, a pilot is not obligated to fly on an airway. It is simply more convenient to do so on many flights. You may select any one of those 360 radials on which to fly, appropriate to your departure airport, your route, and your destination airport. In this example flight from Lake Tahoe Airport to the Truckee Tahoe Airport via the Lake Tahoe VOR, you can use the VOR system of radio navigation. You do this by selecting the reciprocal of the 122-degree radial as the inbound course to the VOR, since radials are always outbound from the station. Then turn outbound on the 012-degree radial to take you directly to Truckee Tahoe Airport. As an example of in-flight navigational use of the VOR, we shall plan and execute a flight from Oakland Airport to Columbia Airport in the foothills of the Sierra Nevada mountains, where a restored gold rush town is within walking distance of the airport. We'll fly via the Stockton VOR. Let's draw the course on the chart. We plan a departure from Oakland Metropolitan Airport. Since Oakland has a VOR on the field, we'll navigate halfway to Stockton using the Oakland VOR. The halfway point is 28 miles, slightly past the city of Livermore, in the vicinity of a 1,700 2-foot peak. At that point, frequency to Stockton VOR, and continue to navigate by reference to its signals for the balance of the flight to Columbia. Reference to the Oakland azimuth, which is highlighted, shows us we'll be flying outbound on the 065-degree radial, and we'll fly inbound to Stockton on the 246-degree radial. Outbound from Stockton to Columbia, the magnetic direction of the radial is 057. We must use a specific procedure with every VOR receiver to gain maximum efficiency and precision in radio navigation. We'll learn these procedures in this lesson. Before we attempt cross-country flight using VOR, we need to learn how the components function. Let's look at the equipment on the Sundowner. Every set must have an on-off switch. On the receivers of some manufacturers, there's a separate on-off switch for both the communications radio and the VOR receiver. We then tune the frequency, using one knob to tune the megacycles and one to tune the tenths or 100ths, dependent upon how many frequencies your receiver offers. Next, identify the station. Think of tune and identify as one word, an inseparable procedure. You don't need to know Morse code to identify the station. Simply compare the code with that written on the chart. The VOR display has three components: the omni-bearing selector, or OBS, the course deviation indicator, or CDI, sometimes known as the left-right needle, and the to-from flag. The omni-bearing selector is the tuning knob which allows you to select one of the 360 radials you wish to use to navigate. It controls the movable azimuth, which has a reference mark, usually placed by the manufacturer at the top of the azimuth. If you plan to fly a predetermined course, such as the 065-degree course we'll be flying from Oakland, you set that course under the index. The additional uses of the OBS we'll learn in our next program. The to-from flag tells you whether the course you have selected on the OBS will take you to the station or from the station. The display is telling you that if you fly following the 065-degree radial, it will take you from the station. Because the 245-degree radial is on the opposite side of the station from the 065-degree radial, if you tuned the 245-degree radial, the flag would tell you that if you turn and fly a course of about 245 degrees, it will take you to the station. You will have no trouble with the to-from concept. Always fly inbound to the station with the flag reading to, and outbound from the station with the flag reading from. You will not have navigational problems using the VOR system of navigation if you make it a rule to always set the OBS on the magnetic course to be flown. The reasons for this procedure will be clarified when we look at VOR orientation. It is very important that you realize that the flag cannot tell you whether you are flying to the station or from the station. The VOR receiver has no capability of sensing the aircraft heading. The flag also has an off indication, which can be giving you one of four messages. The flag will show off when the set is off. It will show off when the signal you are receiving is unreliable for navigation. It may not be strong enough because you are too far away from the station or are too low to receive the station. It will off when you are over the station, as you are flying from to from on a specific course. You are then in what is called the cone of confusion, in which the receiver cannot determine the phase difference. And the flag will also go to off when you are on or when you cross a radial, which is 90 degrees to the radial you have set on the OBS. The reason for this we'll explain in the orientation section. The course deviation indicator, or CDI, sometimes simply referred to as the needle, tells you whether you are on your selected course, in which case the needle is centered, Or your selected course is to your left, or your selected course is to your right. This will be true only if you are using proper VOR navigation procedures. That is, your heading and the selected course are together. Although the accuracy of the VOR receiver in your airplane is probably adequate for VFR flight, let's test it prior to this flight. The FAA provides test facilities at designated airports, which cost you nothing to use. The Airport Facility Directory contains a listing of airports which have these test facilities. In the directory listing, we find that Oakland has a ground check located on the middle of the pad between runways 09 right, 27 left, and 09 left, 27 right. The radial we'll use for our check is specified as the 081 degree radial. So we taxi to the designated point on the airport where we'll see a circle with an arrow pointing in the direction of the VOR. Due to the capabilities of the VOR, we need only taxi into the center of the circle. We do not need to point the aircraft toward the VOR. The radial 081, which we shall use in the check, also painted at the checkpoint site. First we tune the station, which has a frequency of 116.8. We then identify it. We then turn the OBS to the test radial of 081. Since 081 is a radial coming out from the station to the airplane, the flag will read from. If the VOR receiver is perfectly calibrated, the CDI will center. But as you see here, the needle is off-center to the right. Now, to determine the amount of error, we turn the OBS until the needle does center. Then we note the radial on which it's centered. The difference between this radial, 079 degrees, and the test radial of 081 degrees is the error in the VOR, -2. This is within the plus or minus tolerance of 4 degrees allowed for instrument flight. While there are no limits specified in FARs for VFR flight, we do want to make a note of the error on our flight planner. Now we repeat the process by rotating the OBS to the reciprocal of 081 degrees, which is 261 degrees. The flag changes to a 2 indication because this will be a radial to the station from our present position. As you can see here, the needle is off to the left. Now, to determine the amount of error, we turn the OBS until the needle centers. The needle centers on 259 degrees. The error is -2 degrees. If the error were greater than plus or minus 4 degrees, it would be advisable to have the receiver recalibrated in an avionics shop. For flight, recalibration would be mandatory. Since we completed our flight planning and pre-flight check earlier, we are now ready for takeoff on the flight to Columbia. The VOR receiver in the Sundowner is set on Oakland VOR, and the OBS is set on the radial on which we'll fly outbound 065 degrees. We requested and were approved for a right downwind departure after takeoff from runway 27 right. Notice that as we start downwind, the VOR readout is giving us a message. The CDI is on the right, telling us that our selected course is to the right. The flag is on from, announcing that the selected course of 065 degrees will take us from Oakland, which is what we planned. But now the question is, how do we fly onto that selected course? We fly onto the course with a procedure called intercept. Close to the station as we are, an intercept angle of 30 degrees would be adequate. When the CDI is on the right, indicating the course we wish to intercept is on our right, we add the intercept angle of 30 degrees to the 065 degree radial we wish to intercept to establish the heading we must fly in order to intercept. To avoid errors in arithmetic so likely to occur in flight when you are working the problems in your head, use the OBS as an aid. Simply count 30 degrees to the right of 065 degrees. Then we'll turn to that heading as soon as we have completed our departure from the downwind leg. As we approach the 065 degree radial, the needle will start its journey toward center from its position on the far right of the dial. Since it is moving fast when it reaches a point about halfway toward center, turn left toward a heading of 065 degrees, our pre-selected magnetic course. How soon we'll start that turn depends upon the rate at which the CDI moves. Learning to judge its movement requires experience and practice. Now we are outbound from Oakland. The CDI tells us that we are on our selected course of 065 degrees. The from flag tells us the radial selected will take us from the station. But now we note that although we are holding our heading of 065 degrees, the CDI is slipping off to the left. This tells us that our selected course is now to the left. The meaning of this is that we are encountering a left crosswind, which has caused us to drift off to the right. To re-establish ourselves on the selected course, turn 20 degrees toward the CDI. Hold that heading correction until the needle centers. Then reduce the drift correction to 10 degrees left of our selected course. Note now whether this drift correction keeps the CDI centered. It did, so there is no further need for correction. When we reach our planned changeover point, halfway between Oakland and Stockton, we tune the Stockton VOR on its frequency of 116.0, which we noted on the chart. We identify it. Now we see that although we did not change the OBS, since we continue to fly the same magnetic course, the flag reads 2. This is because the radial is on the other side of the Stockton VOR from our position. The course we want uses the 245 degree radial, which will take us to the station from this position. We continue tracking inbound to Stockton VOR, making corrections toward the needle as required should the wind cause us to drift off course. As we come up on the Stockton VOR, the CDI will oscillate, and the to from flag will switch from to off to from. On reception of a definite from, we turn the OBS to our pre-selected course of 057 degrees, which our flight planning determined would take us directly to Columbia Airport. But after the OBS is reset, we notice that the CDI is on the left, informing us that our pre-selected course of 057 degrees is to the left. Now we must again intercept our course as we did departing from Oakland. The recommended method of intercepting the outbound radial when the heading is different from the inbound course is to fly to the station and then turn over the station to the pre-selected outbound course. On our flight, that course is 057 degrees. Flying on this heading will keep us in the same direction as the outbound course. Next, we'll determine our intercept angle if it's necessary. Our flight instructor has suggested a 30-degree intercept close to the station. Since the CDI is on the left, telling us that our desired course is on the left, we must turn to the left to intercept the course. A glance at the azimuth on the VOR receiver confirms that a turn left is a turn to a lesser heading. 057 degrees minus 30 degrees is 027 degrees, our intercept heading. So we turn to 027 degrees. And wait for the needle to start its movement toward center. When it is about halfway to center, we again turn to our pre-selected course heading of 057 degrees, and again monitor the needle closely to make sure it continues all the way to center. If it does not, we may want to roll out before 057 degrees. Or it moves very rapidly to center, or even goes to the right. We may want to roll out before we reach 057 degrees. Small deflections of the CDI are corrected immediately with small heading changes of approximately double the amount of deflection. And how do we know how much deflection we have? A full deflection means we are 10 degrees or more off our selected course. Each mark on the indicator, beginning with the mark in the center, means we are another 2 degrees off our selected course, and the long mark in the center is on course. So we have 2, 4, 6, 8, and 10 degrees. When the CDI is off the scale, we would have to reset the OBS to know how many degrees off our selected course we are. In this example, the OBS tells us that we are 23 degrees off our selected course. This amount of off course would call for a major correction, but a small deflection, such as we have here, would require a correction approximately double the amount of the deflection, or a correction of 6 degrees. We continue to track the 057 degree radial outbound from Stockton, making necessary corrections as we proceed. At a predetermined point, about 15 nautical miles from Columbia, we begin our letdown, assured that through the VOR system of navigation we'll locate the normally hard-to-find Columbia Airport, tucked away as it is in the foothills of the Sierra Nevada mountains. The VOR can be more than merely a handy aid used to augment pilotage navigation. VOR can be a real lifesaver to a pilot who is temporarily disoriented or lost. Assume for this demonstration of VOR capability that we are on a flight from Noss Field to Livermore. The San Francisco Bay's Delta region, with its meandering canals and roads, can make navigation difficult. There is seemingly no system to the roads and waterways. It is in this general area that we have evidently drifted off course due to an unexpected wind, and we really don't know where we are. There's a bridge below us, but the question is, which one? Our course line crosses no bridge. The solution to our problem is a procedure known as a VOR cross fix. Instead of flying in circles attempting to orient ourselves, we'll hold heading and then locate 2 VOR stations no more than 50 miles from our last known position, but preferably closer. We'll use Sausalito and Concord VORs. We tune Sausalito VOR and identify the station.
Rebel, clear, visibility 15, 0 to south. Bakersfield, measured filling 400 overcast, visibility.
Next, we turn the omni-bearing selector until the to from flag indicates from and the CDI is centered. Now, under the OBS index, we can read the radial of Sausalito VOR on which we are located, 032 degrees. This is our line of position relative to the Sausalito VOR. Next, using our navigation plotter and the sectional chart, we draw this line of position on the chart, aligning the plotter with the Sausalito VOR and the 032 degree radial. We draw the line out as far as we can, because all we know at this point is that we are somewhere on that 032 degree radial. To determine exactly where, we tune Concord VOR and identify it. We then proceed just as drawing our first line of position from Sausalito. We turn the OBS until the flag is on from and the CDI is centered. Now we see that we are on the 244 degree radial of Concord VOR. We draw our second line of position from Concord VOR along the 244 degree radial to the point where it crosses the first line of position. Now we have a VOR fix. We are in this approximate location. It is obvious we have been moving during the time required to determine and draw the 2 lines of position, but we can say with assurance that this is the Carquinez Bridge. This position fix permits us to plot a revised course to Livermore. So we draw it from the point of our VOR fix, determine our true course of 138 degrees, find the nearest isogonic line, 16 degrees 30 minutes, round it out to 16 degrees, easterly variation, which is subtracted from the true course, and we find our new magnetic course of 122 degrees, which will fly to Livermore. We must be aware of the fact that the wind, which initially blew us left of course, is still blowing. We'll probably need some wind correction on the balance of our flight to Livermore. In our next program, we'll learn another use of VOR. We'll talk about ground speed checks. And we'll learn usage of the Automatic Direction Finder, ADF, another very useful navigational aid. In our last program, we successfully navigated our airport. We learned the use of VOR navigation, the relatively simple procedures which are required to keep us on course, and how to determine our position with a VOR fix. In this program, we'll explain further use of VOR navigation, namely as a ground speed check, and introduce the Automatic Direction Finder, ADF, which is a simple but effective navigational aid. On our imaginary flight between Noss and Livermore, we will use the VOR ground speed check. It applies the basic formula, ground speed equals distance flown divided by elapsed time. We select a station as much as possible at right angles to our course. Oakland VOR will supply the radials for this check. We arbitrarily elect to start our speed check starting at the point where the Oakland 010 degree radial crosses our course. We tune and identify the station on frequency 116.8, and then identify by the code. Then we turn the OBS until the flag is on from and the magnetic course of 010 degrees is under the index. The question is, have we crossed the radial yet? The CDI is to the right, indicating the radial remains ahead of us. How do we know this? In our imagination, we turn the airplane to the same heading as the magnetic direction of our selected course. It is now obvious our selected course is to the right. We have not yet crossed the 010 degree radial. At the moment the CDI centers, showing we are crossing the 010 deal. We start timing. Now we select a second radial several miles ahead of our present position. We select the 060 degree radial and draw a line from the VOR across the azimuth along the degree radial to the point where the line crosses our course line. Next, we measure the distance between the two radials. It is 10 nautical miles. We now have the first of the two knowns necessary to solve for ground speed. The second known will be provided by the watch. When we cross the 060 degree radial, the CDI will move to center, indicating we are at our second fix. We now have the second known required to work our ground speed problem, and a time of 5 minutes. Now let's solve the problem using our electronic computer. Now don't panic just yet. You will have a thorough explanation of this and the manual E6B type computer on the next two programs. The electronic computer calculator offers us the answer to this problem without having to do a lot of heavy mathematics. First, turn on the computer. Then activate the time, speed, distance mode. Then we enter 10 nautical miles as our distance. And our time is less than 1 hour, so we depress the T button to enter 0 hours, then the 5 for 5 minutes of time, and ask the computer to compute for ground speed. Our answer, 120 knots. We have learned VOR navigation to and from stations, VOR position fixes, and VOR ground speed checks. Yet these are only a few among those of this versatile radio. For descriptions of other in-flight applications of the very high frequency omnidirectional range, refer to Chapter 13 of the textbook, An Invitation to Fly. In addition to its VOR, many airplanes are equipped with another navigation radio called an automatic direction finder. This radio receives stations called non-directional beacons, broadcasting in the 190 kHz to 1750 kHz band. Non-directional beacons are indicated on aeronautical charts by a circle of magenta dots surrounding a small dark magenta circle. The symbol indicates the geographic location of the NDB. Somewhere near the symbol we locate a box. The box contains data about the facility. In the example of the Fresno Chandler NDB, we see that it broadcasts on a frequency of 44 kHz. Its identification is FCH. The small box in the corner indicates the NDB also transmits a continuous taped weather broadcast. Commercial broadcast stations, transmitting on the low and medium frequency bands, are sometimes indicated on the charts. If the frequency is given, you may tune your ADF to those numbers and then navigate to or from the station. The station's geographical location is indicated by an obstruction symbol and the name of the station. KNBR transmits on 680 kHz, as shown in the boxed information. We don't recommend broadcast stations for ADF navigation because only a few are shown on aeronautical charts. A serious deficiency in using commercial broadcast stations as navigational aids is that they often broadcast call letters only once every 30 minutes. But broadcast stations may be useful in flight for more purposes than just listening to ball games. Your ADF could be very helpful in locating an airport in poor visibility conditions. A typical ADF system consists of the ADF receiver, the bearing indicator, the loop antenna, and the sense antenna. The ADF receiver and bearing indicator are located in the cockpit, and the antennas are located on the airframe. The automatic direction finder indicates in which direction the station is located. This direction is shown in relation to the nose of the airplane. In this example, a pilot is flying on a heading of 0 degrees. The 0 marking on the ADF indicator represents the nose of the airplane. She tunes her ADF receiver to an NDB and watches the ADF needle turn from 0 to 30 degrees. fly to the station, she would then turn the airplane to the right 30 degrees until the ADF needle reads 0, and then she would fly directly to the station. To tune a station, turn the radio's function switch from off to the receive or antenna mode. This tunes the ADF mode which provides the best reception. Then we tune the frequency of the desired station and turn up the volume until we can establish an identification. The identification is broadcast continuously on NDBs. Now we turn the function knob to the ADF mode, which activates its navigational capability. The arrow on the end of the bearing pointer will now indicate the direct non-directional beacon as relative bearing on the bearing indicator. If the arrow on the pointer is in the upper half of the dial, the station is ahead of the airplane. If the pointer is in the lower half of the dial, the station is behind the airplane. If the pointer is on the right, the station is on the right. If the pointer is on the left, the station is on the left. The dial of the Sundowner's bearing indicator can be rotated. This makes the arithmetic of ADF navigation easier. However, the FAA private pilot written examination is not as modern as the Sundowner. The exam shows only older ADF bearing indicators with a fixed dial. To prepare you for the exam, we'll set the dial on 0 and allow it to remain there. To use all of these components, we must first learn the language of ADF navigation. The terms we'll learn are relative bearing, which is the angle between the longitudinal axis of the airplane, a line drawn from the nose to the tail, and a line drawn from the airplane to the radio station. Relative bearing is measured in a clockwise direction and is stated in degrees. In this diagram, the relative bearing is 220 degrees. But relative bearing does not tell us all we need to know to navigate to the station. We also must know our magnetic course, called magnetic bearing, to the station. Magnetic bearing is the angular relationship between magnetic north and a line extended from the bearing pointer on the ADF to the radio station. We determine the exact magnetic bearing by working this simple formula. Magnetic heading, as shown by the heading indicator or by the magnetic compass, plus relative bearing, as displayed by the ADF, equals magnetic bearing to the station. In this example, the magnetic heading, as shown by the enlarged diagram of the airplane's magnetic compass, is 037 degrees. The relative bearing, as displayed by the bearing pointer, is 310 degrees. The sum of these two numbers is the magnetic bearing of 347 degrees. Let me show you how this works. An airplane maintains a magnetic heading of 030 degrees. The ADF receiver is tuned to an NDB located somewhere to the right of the airplane. The ADF needle turns clockwise and points to 60 degrees. Because we want to determine where the radio station's location is relative to the airplane's heading, we use the formula magnetic heading plus relative bearing equals magnetic bearing. Fill in the known values. Magnetic heading equals 30 degrees, relative bearing equals 60 degrees. Total value, or the magnetic bearing, equals 090 degrees. On this bearing, the pilot can home into the station. This means the pilot would turn the plane to the right until the ADF needle reads 0 and the compass reads 090 degrees. But how do we navigate using our automatic direction finder? We'll plan and fly a flight from Palo Alto to Antioch by way of the Riga non-directional beacon in Livermore. We shall use ADF navigation exclusively, utilizing the Riga NDB for the entire flight. Take out your sectional chart and locate Palo Alto Airport at 37 degrees 28 minutes latitude and 122 degrees 7 minutes longitude. Riga NDB is east-north Palo Alto near the Livermore Airport at 37 degrees 41 minutes latitude and 121 degrees 31 minutes longitude. Antioch Airport is 37 degrees 57 minutes latitude and 121 degrees 47 minutes longitude. Now, let's draw the course on the chart. After some rapid computations, we determine our course to be 042 degrees from Palo Alto to Riga and 326 degrees from Riga to Antioch. We'll be flying beneath the floor of the San Francisco Terminal Control Area for a short distance of the flight. Let's use our San Francisco area chart to see how the TCA affects our flight. Immediately after takeoff from runway 30 at Palo Alto, we fly into segment C. But since we are climbing from an airport with an elevation of 25 feet and will be making a right turn at 400 feet of altitude, our standard departure, we will soon be into segment D. Thus, a cruising altitude of 3,500 feet will be satisfactory for the flight to Antioch. Shortly after takeoff from Palo Alto, we tune the Riga non-directional beacon and identify it. We verify that this is Riga. Note that Riga has a two-letter identifier, while most NDBs have three-letter identifiers. This is because Riga is a compass locator, an NDB, which is part of an instrument landing system. We are able to receive Riga NDB shortly after takeoff from Palo Alto because low frequency's most important advantage over VOR navigation is that it is not dependent on line of sight for reception. At night, the low and medium frequency bands will sometimes be affected by signals bouncing off the ionosphere, causing them to be received at great distances. For this reason, when using ADF at night, be very sure you're receiving the correct station. After takeoff from Palo Alto, we depart the traffic pattern northeast bound. Then turn to our planned course of 042 degrees. However, if we merely turned to that heading, it's very possible we would only be flying parallel desired course. If so, we would not intercept it. We interpret the bearing indicator, which tells us the relative bearing is 003 degrees or 3 degrees right. Obviously, we must turn right to fly onto that course. The question is, how much must we turn? To intercept efficiently, we recommend a 30-degree intercept angle. This 30-degree intercept angle is a general rule of thumb number which has been found effective for an ADF intercept. So we will turn the airplane toward the needle 30 degrees plus the number of degrees the needle was deflected for a total of 33 degrees to the right. We'll now add 33 degrees to our heading of 042 degrees. The intercept heading is 075 degrees. Why did we add the interval of 33 degrees rather than subtract it? Because at any time our desired course is to the right, we must turn right to intercept it. As we turn right, the compass numbers increase. And when we are turning toward heading numbers which are greater, we are adding. If our desired course is to the left, we must turn left to intercept it. And when we are turning toward heading numbers which are decreasing, we should then subtract. We make a turn to intercept heading of 075 degrees. This turn causes the ADF bearing pointer to move to the left of the top index, because now the station is to the left of the nose. Note the position of the bearing pointer. We continue to fly this heading until the bearing pointer moves to the left an additional 33 degrees, which is the equivalent of our intercept angle. This is the signal that we have intercepted the inbound course of 042 degrees. The fact that we are on course is verified when we turn to our desired course of 042 degrees. This causes the bearing pointer to move to the nose position, or 0 on the dial. The message we received from the ADF is that Riga NDB is now directly ahead of the nose of the airplane. If there were no wind blowing, we would continue to fly any heading necessary to keep the bearing pointer on 0. This would take us on a straight line to the station, but it is a rare flight in which some wind is not encountered at cruising altitude. Wind will cause us to drift off course. We could fly inbound to Riga NDB, keeping the bearing pointer on 0, even without correcting for drift. But this would cause us to fly in a curved course to the station, an inefficient fly. This procedure is called homing. Since homing is inefficient, we should plan to correct for wind drift. To detect drift, we must be very persistent in holding our heading. Then we observe the ADF needle to interpret any movement it may make. We now see that the needle is moving to the left. This means that we have drifted to the right, because the NDB is now to the left of the airplane's nose. Next, we must interpret the number of degrees of drift. We note that we have drifted 10 degrees to the right. If we were to turn only 10 degrees to the left, we would be homing to the station. Instead, we want to establish a wind correction angle, so we double the amount of drift shown by the ADF bearing pointer. This is another rule of thumb number used for correction. This change causes the ADF pointer to move from 10 degrees to the left to 10 degrees to the right, and will take us back toward our course line. Continue flying until the pointer shows an additional 20 degrees to the right, our total heading change. We are now back on course. We then take out half of our heading change from our magnetic heading of 042 degrees to leave in a wind correction angle of 10 degrees. Our new course heading is 032 degrees. This procedure is known as ADF tracking. As opposed to homing, we have established a wind correction angle. We'll now continue inbound to the station on our course line to the Riga NDB. Over the station, the needle will start its swing to the 180-degree position. This is our indication that we're in the station. When the needle reaches 180 degrees, we must now intercept and track outbound on our course of 326 degrees to Antioch. We must track outbound because if there is any wind and we simply keep the bearing pointer on 180 degrees, we will never reach our destination. Our magnetic course from Riga to Antioch Field is 326 degrees. We will thus intercept and fly outbound on the Riga non-directional beacon's 326 degree bearing. So now we turn to our outbound magnetic course of 326 degrees and note that the tail of the bearing pointer is to the right, while the arrow of the pointer is to the left, telling us the station is left of the tail. So this indication directs us to turn left away from the tail of the pointer to our desired course. A 45-degree outbound intercept angle is recommended for efficient outbound interception, another rule of thumb. We will use a 45-degree intercept for this exercise. Our heading of 326 degrees minus the 45-degree intercept gives us an intercept heading of 281 degrees. We now turn left from our present heading of 326 degrees to the intercept heading of 281 degrees. This turn causes the tail of the bearing pointer to move even farther away to the right, and the arrow to move even farther to the left as it responds to the airplane's position, because we have now increased the relative bearing. We continue to fly 281 degrees, a 45-degree intercept angle, until the tail of the bearing pointer moves to the 45-degree position. We have now intercepted our outbound course to Antioch. And how do we know we have intercepted it? We chose an intercept angle of 45 degrees. When the tail of the bearing pointer reached 45 degrees, interception was assured. Again, we can verify this with the ADF formula. The magnetic heading of 281 degrees plus the relative bearing of 45 degrees equals a magnetic bearing outbound of 326 degrees. We are on the 326 degree bearing of Riga non-directional beacon. Using the tail of the bearing pointer to determine course interception makes the mathematics of the ADF formula simpler. We are on our outbound course. Now we turn from our heading of 281 degrees to our outbound course of 326 degrees. Watch the bearing pointer for any indication of wind drift which would cause it to move away from the 180 degree position. The arrow is moving to the left. This means the station is now to the left of the tail position, because we have drifted to the right. It is now obvious we must correct to the left. To correct, we proceed as we did when correcting inbound by doubling the indicated drift of 15 degrees with our correction. So we turn left 30 degrees from a heading of 326 degrees to 296 degrees. This turn causes the bearing indicator to deflect even farther to the left because we have increased the relative bearing, the angle between the longitudinal axis of the arrow and the station. We maintain 296 degrees until the bearing indicator points to 210 degrees, 30 degrees from our 180 degree desired position. Indicating we are back on the 326 degree bearing. Then turn right 15 degrees. To leave a 15-degree wind correction angle with the bearing pointer pointing to 195 degrees. Once the wind correction angle is established, that is the indication we want to maintain with small corrections to complete our flight to Antioch Airport. And so, thanks to a small black box called the automatic director, another flight is efficiently navigated and successfully completed.